In this video, let's take a look at a one sample hypothesis test for the mean when the variance is known for a left-tailed test. In this example, we're looking at data on energy consumption. So in an effort to reduce electricity consumption during peak periods, a public utility company has increased its residential rates between 8 a.m. and 5 p.m. Historically, the average residential consumption has been 2,000 kilowatt hours per month. We're going to use hypothesis testing to determine if the new pricing policy has increased consumption based on a 0.05 level of significance. We have data from all 5,632 customers, and that equated to a mean of 1,994.35 and a standard deviation of 153.26. Since we're testing the mean, assuming our variance is known and performing a left-tailed test, our null hypothesis is going to be that the mean is greater than or equal to mu naught. Our alternative hypothesis then will be that the mean is less than mu naught. Given the information in the equation, we know that our mu naught, which is what we're testing, is 2,000. Our x bar is from our data, and that value was 1,994.35. Our standard deviation was also given to us as 153.26. The n value is the number of data points that we have, and we had information on all of the households, which was 5,632 households. Our z table will be based on our level of significance. In this case, we're doing a left-tailed test, and our value was 0.05, so our z value is negative 1.645. For our z calculation, we're using our calculation for the z value, which is x bar minus mu naught, divided by our standard deviation, which is divided by the square root of our sample size. So in this case, our x bar is from cell B21 minus mu naught from cell B20, all of that divided by our standard deviation from cell B22, which is divided by the square root of our sample size, which was in cell B23. So that gives us a z calculation value of negative 2.767. When we look at the distribution, our z value is negative 1.645, and our z calculation falls to the left of that since it's negative 2.767. Therefore, we're going to reject our null hypothesis. So we can set that up with our logic that if B26, which is our z calculation, is less than B24, which is our z value, then we're going to reject our null hypothesis, which is the case for this example. Otherwise, we would fail to reject the null hypothesis. So we know that we're going to reject the null hypothesis that our average is greater than or equal to 2,000. We can also calculate our p-value to understand what level of confidence we have with these results. We can do that with our norm.s.dist function based on our z calculation. And in this case, our p-value is 0.0028, which is very small and definitely less than our value of 0.05, so we're very confident within our results.